Now we're going to learn a rule that we don't learn until later in the curriculum, but because you're likely watching this towards the end of the year and you'll have already learned these concepts, I'll talk about it now. So this is called L'Hopital's rule. Let me open a whiteboard. So L'Hopital's rule says that basically if we have a limit, the limit as x approaches c, just to generalize it, but c could be any number, it doesn't matter, of f of x over g of x. See what this means? If we have x squared minus 3x plus 5, doesn't matter. It's just some set of values of x on the top and some set of x values on the bottom. Then this limit equals the limit as x approaches c on the top of the derivative of f at c. So over the limit as x approaches c, g prime of x. So this really simplifies things for us because derivatives can, if we have x to the fourth, or even x squared, taking the derivative makes it 2x. And then if we take another derivative, we just get 2. And 2, if that's in the denominator, then we never need to worry about an irremovable discontinuity or vertical asymptote because the bottom is always just going to be constant. So this could work to our favor in horizontal asymptote problems. So an example of a horizontal asymptote problem is this up here. So there's a rule for this that'll help you do it a lot quicker than taking so many derivatives. But I'd like to show you where it comes from. So if we look at the leading term, we know that if we take a bunch of derivatives until this x to the fifth just becomes a constant, then we know that everything here, the 7x cubed, the 2x squared on the bottom, all of these are just going to cancel out. They're just going to go to 0 from so many derivatives. So we can ignore these. And L'Hopital's rule, if it doesn't work once, you can just repeat it and keep going, doing more L'Hopital's rules until you have constants. So if we look here, the degree of the leading term, which just means whatever exponent it's raised to, the highest exponent on the top or the highest exponent on the bottom, it's the same on the top and the bottom. So if we take a bunch of derivatives until that x to the fifth just goes to a constant, then it's going to be a constant over a constant, which is good for our limit purposes, especially if it's going to infinity, like in a horizontal asymptote. So we don't actually need to take so many derivatives because we know that this exponent just keeps hopping down. We'll get 5x to the fourth, and then this 4 will hop down. We'll get 20x cubed. But there's a simpler way to write this, which is 5 factorial. You don't really need to know this, but this just means 5 times 4 times 3 times 2 times 1. And just to save you some trouble, this is 120. So when we take this x to the fifth and make it a constant, then we're going to be left with, we're going to be multiplying that coefficient 3 by 120. So we'll have 3 times 120 over, and if we look at the bottom, we also have x to the fifth. So we'll have 2 times 120, and these just cross out, and we're left with 3 over 2. And it doesn't matter what we're approaching. If we have y equals just a number, that's just going to look like a horizontal line. So the limit everywhere is just whatever that number is. So now if we take the limit as x approaches infinity of 3 over 2, it's just always going to be 3 over 2. So the answer to this problem is 3 over 2. Just because we took all the derivatives and we were left with 3 over 2, which is 3 over 2 everywhere. It doesn't matter if we're approaching infinity. And that's how you find horizontal asymptotes. But instead of taking all these derivatives, it might not always be this simple. We could have a cosine in the numerator or some other strange functions. So what we're going to do here, if you know that the degree of the top and the bottom is the same, like here it's 5, the exponent is 5, the exponent is also 5, then like what we just saw before, we just take these coefficients and divide them. So 3 up here, 2 down here, 3 over 2. So it's that simple. You don't have to take so many derivatives. You can just do that. Now, if instead this was x to the 6th, then the top is higher than the bottom. So if we took 5 derivatives, the bottom just goes to a number, but the top still has an x in it. So we'll have 3x over 2, I believe. 3x over 2. And now if we take x to infinity, this isn't going to stop because there's still an x here. So 3 times a really big number is going to be a really high number. But the 2, it's still only being divided by 2, which doesn't do much compared to that being multiplied by 3. So this does not have a horizontal asymptote, or you could say that it has a horizontal asymptote at infinity, which isn't really that significant. It could appear either way, but you're never going to have to decide between if it's approaching infinity or if it doesn't exist. So if the degree of the top is greater than the degree of the bottom, then the limit does not exist. It approaches infinity. But now, instead, if we had a 6 on the bottom instead of a 5, then we have 3 over 2x, because the 120s cancel out as we saw before. And now if we take 3 over 2 times a really big number, 3 over infinity, let's say, as you divide by bigger and bigger numbers, the number just gets smaller. So as we approach infinity, limit as x approaches infinity, I'm writing on the letters, but that just goes to 0 because it just keeps getting smaller, and we assume that it approaches 0 in the long term. Okay, so that's how you find horizontal asymptotes.